So in the last set of videos, we took a look at the consequences of energy conservation. And in the series prior, we had taken a look at momentum conservation. There is one situation where the two of these can both be in play, and that's in what's called an elastic collision. In an elastic collision, in addition to momentum being conserved, it is also the case that the kinetic energy remains the same after the collision as before the collision. Now, how do we know? So this is the definition of a collision being elastic, is one that also conserves energy across the collision. How do we know when a collision is elastic? Well, first rule of thumb is to first off remember that to a physicist, a collision does not necessarily involve physical contact, just a redirection of velocities. So for instance, any interaction involving the fundamental forces of nature, let's say two planets interacting gravitationally as an example, would be an example of an elastic collision. It's also situations like, say, billiard balls and things like this, although there is some loss during the collision to heat and sound. The losses in billiard balls are fairly minimal. And so if an object doesn't particularly heat up during a collision and it's not making big, huge noises during a collision, for instance, if you shoot one billiard ball into another, you just hear a little click. The collision can be well approximated as elastic. So those are the two regimes that we have. So with this additional constraint, potentially, if we're looking at a collision here in 2 dimensions and the energy conservation, potentially we could be solving for up to 3 unknown quantities at once, but that gets to be a real mess. So for my purposes, I'm going to confine this to looking at a specific case of one-dimensional collisions. With a stationary target. Now, this may seem horribly restricted, but it turns out that we can still do quite a bit with this. So the sort of situation I'm envisioning is before we have object 1 moving in at velocity v1 initial, and we're constraining this to just be in 1 dimension. It collides with an object 2 here, whose initial velocity is at 0. Now it turns out if the system you're looking at, if you got 2 objects that are they're both moving in 1 dimension that are going to collide, what you can do is you can always do a reference frame transformation to a frame where the second object is seen as stationary. So that's why this isn't as big of a deal as it may seem. You transform into that frame, do the collision, then transform back out. I'll do a bit of an example with that a little later. So that's the before, and then afterwards, it'll depend on the relative masses, whether M1 keeps moving forward or not. It might bounce backward, it just depends. But let's just say for the sake of argument here, V1 final is pointing forward, and object 2 is flying away at V2 final. And again, because this is all one-dimensional, we'll go back to my trick of taking care of the direction signs when you substitute numbers. So all the formal mathematical signs in front of the symbols will be positive. Okay, so let's look at the consequences of this being an elastic collision. So we have to satisfy 2 things simultaneously. One of the things we have to satisfy is that the final momentum, equal the initial momentum. So we can write that as m1 v1 final, that's the final momentum of object 1, plus m2 v2 final, that's the final momentum of object 2, equals m1 v1 initial. And we don't have to add anything for object 2 because we're only looking at the case where object 2 is stationary. So initially it would not have any momentum. The other requirement is that the final kinetic energy equal the initial potential energy. So in that case, we can say that the sum of the kinetic energies after the collision, so 1/2 m1 v1 final squared is the kinetic energy for object 1, plus the kinetic energy for object 2 after the collision, 1/2 m2 v2 final squared, equals the kinetic energy before. Well, object 2 is at rest, so it doesn't contribute. All we have is 1/2 m1 v1 initial squared. Okay. Now, this is one of those cases where you can do a bit of algebraic manipulation and then come across something interesting. So it's always useful to remember that whenever we're writing these physical relations, they are statements about nature, and we can often learn a lot from them by remembering that the symbols stand for things and asking how would I put the relation that I see back into spoken language, for instance. So let's go and take a look at the momentum conservation part first. In fact, let me color code these real quick. Let's make the momentum conservation blue, and we'll make the energy conservation red, just so we can follow. Or we'll make it pink, just so we can keep our thought processes straight. Okay, so let's take our momentum conservation relation. I can rearrange this to put all the terms with m1 on one side and all the terms with m2 on the other side. So let's do that. That would give me m1 v1 final. I'd have to subtract m1 v1 initial from both sides, so minus m1 v1 initial equals, and I would also have to subtract m2 v2 final from both sides, minus m2 v2 final. And then we can take a look at that, and we can pull out an m1 from each of these terms. So this will give me m1 v1 final minus v1 initial equals minus m2 v2 final. Okay, we'll put a pin in that for a moment, and we'll switch over to looking at the energy conservation. We'll do the same trick for the energy conservation, put all the terms with m1 on one side and all the terms with m2 on the other side. But before we do that, the first thing we can do is just plain multiply the whole equation through by 2 to make all the 1/2s go away. So let's just do that for a second. m1 v1 final squared plus m2 v2 final squared equals m1 v1 initial squared. So that's just multiplying the energy conservation through by 2 just to make the halves go away. Now again, we'll group all the m1s to one side, all the m2s to the other side. So get all the m1s together, m1 v1 final squared. I'll have to subtract m1 v1 initial squared. And I'll have to get the m2 to the other side, I'll have to subtract m2 v2 final squared from both sides. And again, we can group out the m1 just like we did before. We'll have v1 final squared minus v1 initial squared. That'll equal minus m2 v2 final squared. All right, now we remember from our algebra classes that if I have a quadratic of the form a squared minus b squared, that factors into a plus b times a minus b. So same deal here. This will factor into m1 v1 final plus plus v1 initial times v1 final minus v1 initial. That is still equal minus m2 v2 final squared. All right, let's actually move that over onto the next page. There we go, tidy that up. Now, what we can do is we can look at the momentum conservation bit here, and we can divide both sides of the equation, of this equation, by the matching sides of this equation. So as I divide both sides by the same thing, that's perfectly legal, and these two things are the same thing, just written differently. So we'll go ahead and put in a couple fraction bars here. All right, and then we'll take this left-hand side here, copy, paste, and then we'll do the same thing with the right-hand side. Copy, paste. All right, so now when we go and look at this, let me switch over to black again. M1s cancel here, and the terms where these things are subtracted cancel. Here the plus signs cancel, the M2s cancel, and 1 power V2 final drops out as well. Okay, so now let's rearrange this to get the finals on one side and the initials on the other. So this will give me V1 final, I'll subtract V2 final from both sides, equals, now I'll subtract V1 initial from both sides, minus V1 initial. This relationship does not get nearly the love it should from most books. It is a super useful relation, and one that the books don't really tend to mention a lot. Some of them do, to be fair, but a lot of them is just a stepping stone to getting the relations for what the final velocities of the two objects are. But this is where you might want to sit down and just ask yourself, in fact, go so far as to pause the video and ask yourself, how would you physically interpret this relationship? So pause the video for a sec and then get back with me. Okay, so when I'm looking at the V1 final minus the V2 final, that is a relative velocity of approach. So for instance, just to make it concrete, let's say V1 find, that these were two cars or something like that. Or I should say relative velocity of recession in this case. So let's say you have two cars going down the road. They've passed each other already. The one is heading north at 60 miles an hour. The other one's heading south at 60 miles an hour. So my V1 final will be plus 60. My V2 final will be minus 60. I get 120. And I would interpret that as the two cars are separating at a rate of 120 miles an hour. The same is true on the right-hand side. Keep in mind V2 initial was 0. So this is the velocity of approach. So the minus sign is just to keep into account the fact that after the collision, the objects are coming apart, and before the collision, they're coming together. So this minus sign is just to switch from coming together to going apart. But if I just think about the speeds, what we can say is the relative speed let's write that a little better. EED of recession after the collision, equals the relative speed of approach before the collision. So just like, again, the example, before a collision, if you had a car driving south on the freeway at 60 miles an hour, another one driving north at 60 miles an hour, it'd say, hey, they're approaching each other at 120 miles an hour. So this is the deal. In any elastic collision, the relative speed of recession after the collision is equal to the relative speed of approach before the collision. And this is true regardless of the masses of the things. So it's a very handy result to have. If you know your V1 initial, if you somehow can find your V1 or your V2 final, you instantly know the other one for free, because you know that the relative speed of recession after the collision has to equal the relative speed of approach before the collision. We'll do an example in a moment. Now, after we get this relationship, the usual thing to do is take this, solve it formally for V2 final, stick it back into the momentum conservation relation here, solve for V1 final, then take that solution, substitute back into the energy conservation, get the solution for V2 final. So I will spare you the algebra for that and just get straight to the result. The result says that V1 final will equal M1 minus M2 over M1 plus M2 V1 initial. And V2 final equals 2M1 over M1 plus M2 V1 initial. Now, if both objects are moving, what you do is you first transform to a frame where object 2 is stationary. You use these relations, and then you transform back into the frame that you care about. And again, we'll talk about that in a bit as well. So let's look at this bit right here, M1 minus M2. If the two objects have the same mass, if object 2 is stationary and they have the same mass, and when object 1 comes in, M1 minus M2 will be 0, and the first object will come to a dead stop. But let's say that M2 was huge. Like, let's say you were bouncing a super ball off the Earth. Super ball weighs, maybe 30 grams or something like that. The Earth, an awful lot more than that. Well, in that case, M1 being the mass of super ball is basically 0. And so what you get is minus the mass of the Earth, basically, in the numerator, and plus the mass of the Earth, basically, in the denominator. So we just flip the sign and say that you bounce off as fast as you came in. So those are two extremes. There's also, what if M1 is a lot bigger than M2? Well, then we can kind of ignore the right-hand side, and what we get is that you basically just barrel right on through. So in the example of a semi hitting a fly or something like that, the semi doesn't really slow down to speak of. All right, so let's just do a quick example of that, just to have some concrete numbers to this. So let's go ahead and fire, and you will need to fire it to make this work. A tennis ball, we'll say it's 0.1 kilograms. We're going to fire that into a bowling ball. We'll say that one's 5 kilograms. We'll say that the tennis ball is going at V1 initial is 100 meters per second. So yeah, you had to launch this out of a potato cannon or something like that. Please do not try this at home. And V2 initial is 0. We'd like to know afterwards, what are the velocities of the objects afterwards? So it's v1 final and v2 final. Well, certainly here, the tennis ball weighs a lot less than the bowling ball. So that means we expect it to have a speed of less than 100 meters per second, but probably not a whole lot less. And to be going to the left. So we're expecting a negative v1 final, and then we expect v2 final to be going to the right, and probably not terribly fast because it's pretty darn massive. So all right, let's go and crank it through. So v1 final equals, well, m1 is 0.1 kilograms minus 5 kilograms. And this would be 0.1 kilograms plus 5 kilograms times 100 meters per second. And to one whole digit, that's about, negative 96. So to two figures, that's about negative 96 meters per second. Now you could go and plug into the other relationship to get v2 final, but this is where that speed of recession equals the speed of approach line. If we look at that, we would be saying, oh, v1 final minus v2 final is minus v1 initial. So then we can rearrange to get that v2 final is v1 initial minus v1 final. v2 final is v1 final plus v1 initial. So v1 final is minus 96 meters per second. v1 initial is plus 100 meters per second. So to one whole figure, we get about 4 meters per second. 96 plus 4 is 100. Alrighty. Now, there's another fun application of this, enough to what I like to call the slingshot effect. Here, there's a classic demonstration, which I can't show you here, but I can at least talk about. Where what you do is you take like a small super ball and you stick it on top of like a big basketball or something like that. So M2 here is a lot less than M1, and that's my M1. And you let them fall together as a stack. So the super ball on top of a basketball is a classic one. Now if you let them fall together as a stack, when we look at the basketball here, so this is what we're going to think about for the moment. The basketball is going to hit the earth. The mass of the earth is a lot bigger than the mass of the basketball. So if, say, we're coming in with velocity v1, we will leave v1 initial. Well, basically, when we bounce back off the other way, v1 final is basically going to be minus v1 initial. Okay. Now, in the split second after the basketball is bounced up, the super ball is still going down. So let's think about what that's meaning. So in this instant here, when the super ball is still going down, basketball is still going up, the super ball is going down with a velocity v2 initial that was equal to v1 initial, because they're falling together initially. And now this is coming up at minus v1 initial. So here's where we can go ahead and do our trick of boosting out. So if we switch to a frame where the basketball is stationary, so going to the basketball's frame, we look at this and we say, hey, if this one's going down at V1 initial, this one's going up at V1 initial, they're approaching at V2 initial. So if the basketball's saying, hey, I'm sitting here stationary, it's seeing the super ball go in at 2 V1 initial. And since the basketball is a lot more massive than the super ball, when the super ball bounces off, in the frame of the basketball, it would bounce off at 2 V1 initial in the other way, minus 2 V1 initial. Well then, finally, we go back to the Earth frame. We say, but really the basketball's moving up at V1 initial, so minus V1 initial, and they have to separate at 2 V1 initial. So we conclude that after it's all said and done, this is going up at minus V1 initial, and the super ball, in order to separate at 2 V1 initial, has to be going up at minus 3 V1 initial. So what we get is in this collision, the ball goes at, the super ball winds up bouncing off at triple the speed. You can work out that this means that it should fly about 9 times higher than the height it was dropped from, a little bit less. A fun application to this, it gets sort of the nickname the Slingshot Effect. Have you ever wondered how satellites launched from, artificial satellites launched from Earth, make their way out to the farthest reaches of the solar system? There are 2 ways you can do it. The problem here is that as you head away from the sun, the gravitational potential energy of the satellite and sun is increasing, which means that that decreases the kinetic energy of the satellite. So the 2 ways you can do it are, say with the Voyager satellites, if you happen to have some leftover Saturn rockets hanging around from the days of the Apollo missions, you can go ahead and put a modest-sized satellite on top of an absolutely enormous rocket and launch it straight to Jupiter. More typically, though, that's not how we do it. And even to get past Jupiter, they had to use the same trick that we do usually to even get to Jupiter in the first place, which is you do a strategic flyby of a satellite with a planet. So as the satellite flies past some planet, so let's say here's the velocity of the planet, it's exactly the same thing as the super ball and the basketball. If the satellite, I'll try to draw a satellite, it's not going to go well. Those are supposed to be the solar panels. If the satellite is coming in at V1 initial, when you loop it around, this is technically a collision because the satellite changed direction, and that's all you need to be a collision, even though you didn't smack the surface of the planet. When it flies out, V1 final will be approximately V1 initial plus 2 times the speed of the planet. So you pick up double the speed of the planet. And this is really useful. Now, technically, you slow down the planet a microscopic bit, but it is so negligible you would never, ever, ever, ever notice. But you pick up basically this bit of a boost here where by microscopically slowing down the planet, you can add double the planet's speed to the speed of the satellite as it flies by, roughly. So in the case of most launches, if you're trying to get to the outer solar system, what you do is you first launch the satellite to fly by either Mars or Venus, and you'll have it pick up a series of these gravity assists. That's the more fancy technical term for it. As you go past each of the planets, you keep picking up double the speed of the planet. That increases the kinetic energy of the satellite until eventually it gets to be so big that it eventually shoots off, that it has enough kinetic energy that you can make it across the asteroid belt and over to Jupiter. If you're going beyond Jupiter, you then use a gravity assist off of Jupiter to make it to Saturn and so forth. So you have to wait until you've got fairly convenient planetary alignments, which is why you hear about these deep space missions having very, very specific launch windows. They're waiting for the planets to be lined up just right so that they can pick up all of these gravity boosts. Okay, I will catch you in the next one.